Hello, I'm Sarah.
And I'm Mihaela.
And this video presents our paper, Designing Recommender Systems with Reachability in Mind, for ICML's Participatory Approaches to Machine Learning workshop.
Recommender systems mediate access to information in our digital world. They aim to surface content that will be enjoyed and are primarily designed to accurately predict preferences based on our past interactions with the system. In many cases, they are an effective method for sorting through the deluge of content on the internet.
However, the singular focus on preference prediction has led to concerns of unintended consequences like polarization and radicalization. While other metrics like diversity and coverage have been proposed, they are used in post hoc approaches and do not directly take into account the interactive nature. In this work, we investigate a metric based on ideas of access to information.
For example, if I love to watch cat videos, it is not surprising or bad that I am often recommended videos about cats. But is it possible for me to see a video about a bird instead? What range of options can I possibly see for different permutations of ratings on the left? Which items are reachable?
In this work, we ask the question, can a user choose an input action so that a particular item is likely to be recommended? We'll specifically say that an item I is row reachable if the user can choose an action so that the probability of item I being recommended is larger than row. We therefore define the maximum row reachability for each user and item pair. To compute this value, we consider the internals of the recommender. We will discuss, in turn, the user action space, the score model, and the selection rule.
Within a recommender system, users are represented by their ratings. Some of the ratings can be modified by actions, while others are specified by historical data. The action space is thus determined by the ratings which are mutable.
The rating data is used to fit and update a score model, which we parameterize in terms of the user actions. For example, matrix factorization models predict ratings as the inner product of item and user factors. These factors live in a latent space with initial values determined by historical data for both items and users. When users take actions, their latent factor is updated. For a large class of preference models, this process results in a linear score update rule.
The updated score is used to make a selection. Each item's score is translated into a selection probability. In this work, we consider the class of softmax probabilities parameterized by a factor beta. This class includes uniformly random recommendations as well as top-1 deterministic selection.
We are now ready to show how to compute the main metric of interest, the maximum row reachability. To maximize the probability, we rewrite the following inequality in terms of exponential probabilities. We then rearrange terms and take a logarithm of both sides, and then plug in the linear score model. Using this expression, we formulate an equivalent optimization problem. This is a convex program, and therefore we can solve it efficiently.
To illustrate how these three system components affect the reachability metric, we consider a simple simulated experimental setting with 50 users and 100 items. We suppose that 20% of the ratings are observed and fit a matrix factorization score model. We then investigate the reachability properties for different action spaces and selection rules. We consider selection rules with varying levels beta, and for each beta, we compare against the baseline probabilities of the model predictions based on only historical data. We consider action spaces of different sizes as parameterized by the fraction alpha.
Aggregating over all users, we plot the baseline probability against the maximum row reachability for each user and target item. The no improvement line means that the user actions do not improve the reachability over the system defaults. For small beta, corresponding to a more random selection rule, the values are clustered around this line. For larger values, the maximum row spread away from the line. High baseline probabilities correspond to high baseline scores, but this dependence is not as pronounced for max reachability probabilities. For low, medium, and high baseline items, large values of row max can be achieved. Finally, larger action spaces correspond to larger achievable row max values.
In conclusion, this work makes preliminary progress towards understanding how components of a recommender system affect its reachability properties. Please see our paper for full details.